So bird is basically oh right, my bad. So you got 14 y, and y is going to be like how much you weighed originally. So y is equal to bird. Uh, yes, so y is equal to bird, and since he weighs 10 pounds of bird, you plug in 10 there. It's just the rate is 0 because I'm going to yeah, yeah,
Hey, Miss Brown. All right, let's go ahead and talk a little bit about these questions. Most of you guys got through most of these, so I'm going to go pretty fast at the beginning, a little later at the end. So some people were asking why, that's way too big, why we know to use arctangent in this question. Some of you guys tried to do this as the u on the test, and you might have seen that du is whatever 49 times 2x is. This x is the reason that we need to use arctangent. That x is not in my numerator, so this is why we need to use arctangent instead of being able to use that u as the bottom. Now, the u part is always the one with the variables in it. The a part is always the numbers. What did you guys choose as u? 7x, which makes du 7dx. So I saw a lot of you guys moving this over as a 1/7 to compensate for the fact that our derivative is not just 1. What did you guys choose for a? Perfect. 5 squared is 25. So I have my 1/7 from my u sub, and then was arctangent the one with the 1 over a out front or no? Yeah, so I have 1/5 arctangent of u, which is 7x over a, plus c. I can certainly multiply those two fractions at the front together to get 1/35, or I could just leave it. No, so this guy is the argument of arctangent, so I don't touch him at all. I could combo those, though, at the front. Yep, you're good. All right, let's look at these ones. The particular solutions, these are probably the ones where you're going to spend your most time on round 2, looking at the test this morning. Remember, I can give you absolutely no points if you don't separate your variables correctly. So I'm going to multiply by y, and I'm going to multiply by the dx, so x squared dx. I always move my y's to the left and my x's to the right because the dy and the dx need to be in the numerator. They can't be in the denominator of a fraction. I'm going to integrate both sides. Shouldn't be too hard. 1/2, what am I doing? 1/2 y squared, 1/3 x cubed, and we're going to put the plus c on the x side. It technically doesn't matter, but we're eventually going to solve for y, so that makes it easier. To gather your points more quickly, I would certainly plug my point in as soon as humanly possible. Let's see, that's 4 over 2, 27 over 3, 9. Did you guys get -7 as your c? Perfect. I'm going to plug this guy back in right here. And I'm going to solve for y. Personally, I chose to multiply by 2 everywhere first. Some people use parentheses. It's completely fine. And then I'm going to square root. Now, some people got all the way to here, and you're going to see this highlighting. Yeah, we need a plus or minus. When we create a square root, we get 2 choices for functions. How can I decide which is the correct choice? Yeah, I can plug the point back in. That's kind of the whole enchilada there of plugging the whole point back in. So if I do 2/3 times x, which is 3 squared minus 14, I can simplify the inside of this. Thank you, because that wasn't going to make sense. I was getting a little worried. So that is what? Plus or minus square root of 4. All right, that is 2, but to make it that -2, I need to choose the minus. Now for the square root ones, they're usually pretty easy because y is like plus or minus a singular number. So if you didn't feel like plugging the whole thing in, you can just choose that minus to get that negative y value. So my answer is going to be this function with the minus chosen. If you're doing multiple choice, I would make sure you choose the one with the minus on it. Hint, hint. All right, for this one here, this was our second particular solution of a differential equation. Here, I'm going to divide by the y plus 6 and multiply by the dx. Man, we all need a rest. I feel like we are all sick and tired and sad. All right, how do I integrate this side? Natural log. If I brought this up as a -1 power, I'd be trying to divide by 0 eventually. That's not a good vibe. So we're going to do natural log of y plus 6 like this. Absolute value bars, yes, important. This guy, I believe, is x cubed and then plus my c. Again, to maximize your point values, you're going to plug in your point as soon as humanly possible. That's going to give me natural log of 7 equals 0 plus c. So c is natural log of 7. You don't want to get a decimal. You want to leave it a number. Natural log of 7, that's a fine number. Some people got all the way to here, and you just have one step left to do. Perfect. To get rid of a natural log, I want to exponentiate both sides. So take e to the power of both sides. Technically, when I do that, I am getting plus or minus e to the x cubed plus natural log of 7. And then I am going to subtract my 6. Now, I personally wrote mine out front like this, so it makes sure this looks like an exponent. Now, if I'm looking at this to make sure that this is going to give me a 0, +1, pretty sure I'm going to be using the plus part of that plus or minus because -6 minus something would be negative. You can simplify this part if you want into e to the x cubed times e to the natural log of 7. E to the natural log of 7 is 7, so you could make this 7 e to the x cubed with the -6 being added or subtracted, whatever. What? If I plug in my 0, 1, so I have 1 equals -6 plus e to the 0 cubed plus natural log of 7. -6 plus or minus e to the, let's see, that would be e to the natural log of 7, which is 7. So I have -6 plus or minus 7 equals 1. To make that true, I need to make it the plus. But I figured since without plugging in and doing all of that work, I figured if I had -6 here, I probably should add something if I want the 1 to be positive. All right, so you're more than welcome to leave it like this, or you can simplify that back half if you want to. I would just leave it. All right, the last one, Pert. He's a puppy. Named that for a reason. We are going to use p e to the rt. Does anyone know what part of the question tells me that I'm allowed to use that? Oh, before that. Yeah, Evan. Yeah, proportional to his weight. So his rate of change of his weight is proportional to his weight. Now, Daniel, you were telling me I could plug some stuff in?
Yeah, you can plug in 10 for the
Mm-hmm.
and then you can plug in 0 or you can ton of these visible.
Perfect. So all of these points are going to be time, pounds, time, weight. I actually don't even like to plug this one in because what is 10 going to be equal to? P. And that's going to happen every time. P stands for principal. So 10 is going to be my P value. Sadie asked a good question as we were working on this. She was like, is 10 going to be my P value for the whole question now? Absolutely. We're going to roll with all of the constants we solve for. So the next thing I'm going to try to find is R, so that by the time I get to the end of the problem, everything is just numbers. All right. So I'm going to do 17.2 and my time is going to be 4. So now I'm plugging in 17.2. I'm plugging in the 10 for the P, e to the R times. That should be a 4. I'm going to divide by 10 by moving this decimal point. And how do I get rid of an E? Natural log. It's just like E gets rid of a natural log. Natural log gets rid of an e. They're inverse functions. Then I'm going to divide by 4. I am not going to plug this number into my calculator. I'm just going to leave it gross. Is that my answer? No, I need to plug in one more time. I'm going to be plugging in 7 for t and finding my pounds. So 10 still my p, e is still himself. This weird number is still my r. And then my time is that 7 months old. You're going to plug this into your calculator. If you did, you should have gotten somewhere slightly north of 25 pounds. I would encourage you to, even if you are not going to check this whole answer, I would at least kind of sanity check it. If I got 500 pounds for a puppy, I would be a little concerned. If I got that he was going to weigh less, it's a big puppy. If I got he was going to weigh less than 17.2, I would be concerned because I already know he's growing. He's not shrinking as a puppy. So you want to make sure you're kind of making sense of that answer. All right. Yeah. That's totally fine. Yep. You just left it. Yeah, that's totally fine. So if you leave this unsimplified, I would just be more careful about how you're plugging into the calculator, but that should be fine. Mm-hmm. Yes. Yeah. You could get to, if you wanted a number, yes. If you wanted to just leave it here, I could do that without a calculator, but I'm certainly not getting a number as my answer. That's mathematically equivalent, so I would have said yes. Yeah, you're good to go. All right. So we feeling a little bit better about this one? Technically, no, because I didn't ask you for a simplified answer. I like giving one just to make sense of it, because how do I know this isn't 3,000? But technically, anything mathematically equivalent, unless I ask you to simplify, is good. All right, we feeling good about round 2? Yeah. I could give you a different one for the beginning, but this is kind of the most common differential equation, and it's the only one where we have it memorized. So you probably wouldn't get one that's quite as contextual with like all of these points to plug in. So anything where you're growing or shrinking at a rate proportional to how much is there. So a good example is like chemistry half-life you can do with PERT. You could also do like some compound interest. If I say like your bank account grows at a rate proportional to how much money you have. A lot of the time it's like a growing plant or a growing puppy or a growing bacteria population, something like that. All right, so if you have any other questions, I kind of lit up the first page a little bit with highlighting because there are a lot of places to make small mistakes. That was the USub page. If you want to practice more USub, feel free to come by. I'm more than happy to create some problems, but most of that was rolling well at the beginning of the problems. Most of you guys were just forgetting to integrate or using weird integration rules. So I think the round 2 should be relatively fine. That'll be 20 minutes at the beginning of class next time. If you're not going to be here on Friday, I would highly recommend coming and just getting that done before you leave for spring break. Also, because that test is going on this quarter, you really should, because I'm going to grade it on Friday anyway, unless we talk. So make sure you're getting that done. All right, you guys ready to learn some volume by cross sections? It's so pretty. I think so. I think it's cool. So we're going to be trying to graph something in the XY plane today. So if you can see, we're actually going to do this graph today. Does anyone know what function that is? The red one? Oh, it kind of does look like natural log. That's close. This one's a little bit easier. This is the square root of x. And we're going to use, I think, that dotted line. Yeah, that's good. That's x equals 9. So we're going to be building up different shapes on this guy. Let's see if I can remember where some of these things are here. We're going to do this example as our first example, I think. And We're going to do some different shapes today. So one of the shapes we're going to do, can you see it? It's cute. We can do semicircles. We're going to do some triangles, not equilateral ones, but we'll do some triangles. We'll do some squares. We'll do some rectangles. We will not do anything bigger because we're going to end up integrating an area formula. So we're going to start by figuring out what area formulas do we need to know. So we'll do a couple examples, take a break, do a couple more. That is the shape. What? Probably almost like a circle.
Yeah, right.
Fun fact, this is the second to last set of notes. Yes! Why not?
So do we only have 8.3 and then?
8.3 is gonna be done.
Okay. There's only 3.
I said hey, it was only 3.
I didn't know. Yeah, 8.3 is a little aggressive. Yeah, because I don't want to do 3 days, and then most likely for after the AP test, if we do any quizzes and stuff, it'll probably be like mastery stuff.
We want to say, I don't know a single thing about Louis. Oh, yeah. That's a good one.
All right. So I'm going to tell you where we're taking a break. We're going to do the first page, and then we're going to do these 4, and then we're going to be done for a break. Perfect. All right, so this section I don't think is super duper hard. It is a little visually weird. As someone who also maybe you have great spatial reasoning, I do not. So there are a lot of things I do in this unit to help me with my own spatial reasoning because I can't visualize super great. So I'm going to take a lot of extra steps, not really extra steps, but I'm going to break things into specific decisions. If you decide you can do things faster than me, by all means, you can. But I'm going to break a lot of my decision-making things into a couple of pieces. What this is going to come down to is integrating an area formula. I like to think of integrating as kind of like adding a dimension. So last class when we found area between 2 curves, we ended up integrating like a one-dimensional line, that vertical distance, that f of x minus g of x. So integrating a line got us an area. So here we're going to integrate an area to get a volume. We're going to be finding an area formula for a specific cross-section and integrating that across the region that we're working in. We can do this in terms of x or in terms of y. So neither of these formulas are like really mind-blowing. We're going to more so practice some problems. Now, one thing that's kind of non-negotiable as we go is drawing the region in the XY plane, just like we would have last time. So we're going to make sure we do that. So I'm going to tell you about some of the shapes that I'm going to use. I will say like 90% of the time on the AP test, your cross-section is probably going to be a square or a semicircle. Like 9% of the time it's going to be a rectangle, and that last 1%, it can be anything. One year I said it was always going to be a square or a semicircle, and then it was an isosceles right triangle with bases to legs. So I don't say always anymore. So in this chart, I'm going to draw a square, a semicircle, a rectangle, those triangles, and then we're going to write an area formula in terms of the base in the XY plane. When I say the base in the XY plane, this a little bit. I mean, okay, maybe not there. I mean like this distance right here. Whoa. All right. I mean right there. So this distance where my shape is like flat on my paper. So I'll do a lot of gesturing today. Hopefully it will make sense. All right, first thing. This is a square. Wow. That's actually one of my better round 1 squares on this set of notes. All right. So one thing about my drawings today, I like to draw everything by hand for you guys and not make super computerized drawings on my paper so that it's imperfect, like your drawing will probably be. So I'm going to call the bottom of this B. What is the area of that square? All right, but if it's a square, b times b or b squared. Wow. All right, let's skip to rectangle real quick. I'm just going to draw a random rectangle. This is my rectangle. Your rectangle could look different. That is technically a rectangle. What's the area of this rectangle? Base times height. Now you may say, that's too many letters. And you're right. So I'm going to make a note. You'll get some info about the height. So I may say something like the height is 3 times the base. We're going to see that one later today. So you'll get some information to be able to plug in there. Now, the semicircle is kind of the most annoying one because when we think of areas of semicircles, we don't generally think of them in terms of like the diameter of the semicircle. Yeah, so let's talk for a second. Hold on. So here's my semicircle. Problem, this whole thing is my base. We usually don't think about that. We usually think in terms of the radius. So what's the area of a semicircle in terms of the radius? 1/2 pi r squared. All right. But let's think about what that radius of this semicircle actually is. In terms of b, what you guys agree with Herbie that the radius of this would be like b over 2, 1/2 b? So a few years ago when I started teaching this, one thing I did was I simplified this formula to kind of get a formula for the semicircle in terms of essentially its diameter. So I'm going to square this 2, get 4, and multiply it by that 2 to get pi over 8 b squared. If you have room in your noggin for a formula, that tends to be a pretty useful one because semicircles are a pretty popular cross-section. Yes. Yep. Yes. Mm-hmm. So when we use it, I'm going to act like a formula. If you don't like that formula, you're more than welcome to use kind of this version. You just have to divide by 2 in a couple of places. All right. Yeah. Yeah. All right. Who remembers what this word means? Isosceles. It's been a hot second. All right. We got 2 of the sides are going to be the same length. Now, we also have right triangles. What does right mean? All right, so we got triangles with 90-degree angles. We got 2 options. One that has the base as the leg, one with the base as the hypotenuse. Now, we could work these out the way that we did with the semicircle. I like actually more so to think of what proportion of a square these 2 triangles are. Because one year when this was actually on the AP test, one of my brilliant students was like, oh, that's just whatever portion of a square. I was like, Jack, you're a genius. All right. So here's my right triangle. The leg is the part that's not the hypotenuse. So an isosceles right triangle with base as the leg kind of looks like that, where this bottom part is B. How much of a square does that look like? Half. What did you just say? Oh. I thought he... a different SH word. All right. So 1/2 B squared. All right. That's okay. It's not like I haven't said that SH word before in my 30. Yeah. Shoot. Oh my God. All right. Shire. Oh my Shire. All right.
Forgive my.
All right, this one I like to think of like an envelope flap, if you will. So I've got my hypotenuse is the base, and my 2 legs are kind of diagonals or parts of diagonals of that square. How much of the square does it look like? 1/4, so 1/4 B squared. So hypotenuse is going to be a little bit smaller because we're a smaller part of that square. We're using the bigger side as our base. And there we roll. I promise you on my test, these are the only ones that I'll expect you to know without giving you a formula. So if I give you some sort of weird, awkward shape, like maybe an octagon, I would give you that formula. I'm not going to ask you for an octagon, but just so you know. Because I don't know the area formula for an octagon. Mm-hmm. All right, so we're going to practice today. We're going to practice just one start to finish. And then one of the ways I really like to do these examples is I really like to show you what's going to happen if I change certain things about the question. So you'll notice this in the 8.3 notes as well. Our last set of notes is that I'm going to take one region in the XY plane and we're going to kind of change how we do it. Today we'll change the shape. Next class we'll change how we're rotating. And by next class, I mean after spring break, because this is the last time I'm teaching you. We're going to do some AP review. Who wants to learn on the Friday before spring break? So we're going to just do some multiple choice practice. All right, so let me roll you through this question. I'm going to roll you through one. This is kind of what a question would actually look like. I wouldn't actually ask you to do like 4 different shapes. So I just want to show you what this would actually look like, just start to finish, one problem. These are a little wordy, so we're going to kind of work through what the words mean and then what it's asking us to do. One thing I do like about these questions is they're generally pretty straightforward with what they're asking for. So we're looking for some kind of keywords. Here we're asked to find the volume of a solid. So again, we want to integrate an area formula whose base is the region bounded between the curves y equals the square root of x, vertical line x equals 9, and the x-axis. So the first thing I need to do is I need to draw a picture. If you don't draw a picture and you ask me for help, the first thing I'm going to tell you to do is draw a picture. We need to be able to see what's going on. So the square root of x is a graph that I would expect you to be able to graph on your own. It's the one that we just saw. Let's talk about some points on it. I graphed one of the points, 0, 0. Does anyone know another point that's on this graph? All right, 9 comma what would be on this graph? Square root of 9, which is 3. Brilliant. Does anyone know another point that's on this graph just for fun? 4, 2. Great. Another one? 1, 1. Great. All right. When in doubt, plug in some points, see what's going on. So I got this graph and bounded by, or just the word bounded. When we see that word, think of like a fence or think of in this room, we're bounded by the walls, the floor, the ceiling, the door if it's closed. So our area that we are bounding is this kind of region in here. I'm going to erase that shading in a second because I'm going to draw some stuff. So that's the same picture that I have on this Desmos graph. This one's got a little bit of perspective, so it's a little bit funky. But you can kind of see that region right there. Now notice there's kind of one cross section, that kind of orange line. That actually is really helpful to draw. So a lot of the time when I do these questions, and I would encourage you to do this as well, I'm going to draw one, in this case, vertical line anywhere in my region, and I'm going to label that my base. Now, the reason I'm drawing it up and down in this case is I see the words at the end of the question perpendicular to the x-axis. Those are actually pretty happy words to see because that means I get to work in terms of x. So I'm going to have x's in my integral. I'm going to have x's in my bounds. That is a happy word to see. Now, if you want, this gets a lot of my students mad. But this is the way I had to do it when I was learning, is I kind of like to draw one of those cross sections in my picture with perspective, kind of like this one. If this makes you mad, don't do it. But I kind of like to draw one of my cross sections as like a square, like it's going out of the paper. That makes a lot of people mad though. I would say at bare minimum, draw that vertical line. All right. Now comes the part where we are going to try to do some actual math. I like to split this into 2 very separate sets of decisions. So I like to start by writing the area formula for each cross section and then integrating that to find volume. So for the area, what shape are we working with? Squares. It says so in the question. We're not going to have to guess a shape. They're going to tell us. What was the area formula for a square? B squared. So now I have to find a value, not necessarily just one value, but kind of a function to put in for B. You guys remember the theme from last class, top minus bottom? It's a theme for all of the classes in this unit. So we're going to take the top thing and subtract the bottom thing. That's why this... Did we do it last unit? Oh, yeah. With bounds, it kind of works the same way. So we're going to take the top function and subtract the bottom function. So that's why this vertical line is a little bit useful. What's that top function? Square root of x. And what is that bottom function? Kind of the x-axis, right? What would you put? 0. Now you may be like, yo, Hefty, why are you writing that 0? To make sure every single time I'm subtracting a bottom function. So you're going to see me write a lot of extra minus zeros, minus things to remind me to make those decisions. I'm going to simplify this real quick. Square root of x quantity squared is just x. I like to do that to do a little bit of sense making. Let's talk about, actually, let me go back to the graph so you can see it moving. Does it make sense that our area formula would be x? I would argue, yeah, a heck of a lot. So algebraically it makes sense, but it also makes sense with where this shape is. If I move the x value to be smaller, so I go closer to 0, what do you notice is happening to the square? Yeah, it's getting smaller. So the smaller the x value, the smaller the square. As I move over here, the bigger the x value, the bigger the square. So if you notice, as I move over to all the way to 9, our area of our shape is 9. So it's a really nice way to kind of sense make if you can try to plug in some x values and see if the size of the square kind of works with the way your brain is thinking. All right, so now that I have an area formula, this one we simplified because this is the only question we're going to do by hand today. Now I like to go to my volume. This really has one decision in it because I'm going to take my area formula and that is my integrand. So really the only thing I'm doing by splitting this into 2 pieces is being able to focus on the area formula and then what's kind of glaringly missing as the choice in this step, the bounds. What did you claim? 0 and 9. Beautiful. I like how you chose the x values here. The x values should be the ones we're choosing since x is in our integral. If you're having trouble with the bounds, a trick I like to do, remember that vertical line we drew? You got to stick your pencil on it and slide it back and forth in the area that we're working with. As far left as I can go in that region is 0. As far right as I can go is that 9. Yes. After our break. All right. Let's go ahead and integrate this by hand. What is the integral of x? What? You have to integrate it first. What's our antiderivative? 1/2 x squared. Some of you guys just refuse to integrate on the test. Maybe try that. All right, then I'm going to put my vertical line to say, hey, I took an antiderivative, but I didn't plug in my bounds. Which bound will go in first? 9. So I'll get 81 over 2 minus 0. For Derek, I will call this 40.5. All right. Now, volumes get a little bigger faster, so you might be saying 40.5. That sounds a little big. We're working with 3 dimensions, so our volume may get a little bit bigger than we expect, but this isn't like 10,000. I'm feeling okay. All right, let's do one more example in terms of x, and then we'll take a break. We're going to change the shape to do 4 different shapes. Not a whole heck of a lot changes based on the shapes. So we're just going to kind of see what happens. Let me show you a graph first, then we'll graph a little bit. All right, so let me see if I can remember. And I'll post this guy if you want to play with this graph. I think it's really fun. All right, we got x squared. Does anyone know where these graphs meet? Yeah, 1, 1. So I'm going to change this b to be 1. All right, this guy is real small. I'll zoom in. Where's my perspective dot? Oh, he all the way over there. All right, so you can kind of see this is a small little region. And we're going to build a bunch of different shapes on top of it so we can see what happens when we change the shape. I also want to show you with this question, what happens if I have a bottom function that's not just like the x-axis? You're going to notice these integrals are going to get pretty complicated pretty fast, which is why a lot of this test, if not all of this test, I will allow you to integrate using the calculator. Just a note for the directions, if it says find the volume, we want a number as our answer. So I may just be our calculator because that's not really the point today. All right, so I'm gonna blow this guy up and I'm gonna draw kind of that leafy shape that we just saw. No, so that is coming from our y equals the square root of x. We're using that a lot in this set of questions because it's an easy graph to graph. They'll tell you in the question. Yeah, so ones I would expect you to be able to graph on your own are like square root of x, x squared, any lines. So like 3x plus 2. Once it gets kind of more complicated than that, I might give you a calculator to be able to graph. All right. We are still perpendicular to the x-axis, which means we get to work in terms of x. We'll work in terms of y after our break. So I'm going to go ahead and draw that one vertical line to represent the base. Again, I'm just drawing that anywhere in the middle of my region. It's not at like a specific place. All right, let's do some squares first. What was the area of our square? B squared. All right, let's talk about B. We're doing top minus bottom, just like we did before. What is the top function here? What? Yeah, this is still square root of x. So we're going to have square root of x and minus x squared. Now, if I actually did want to like simplify this, I'd have to FOIL it out. I can't just square each thing individually. That's going to get real gross real fast. So this would be one where we would shove it in the calculator. All right, I'm going to throw that in my integrand. And I'm going to ask you the bounds. 0 and 1. Now, question, that's this 0 and 1, right? Not this 0 and 1. Yeah. All right. Let's change it up. Semicircles. What was our area formula for our semi? This guy right here. I can set these guys equal to each other if I wanted to. I was just thinking what thing when I square root and square it is the same? 0 and 1. Kind of logic it out. All right, what was our formula for our semicircle? Anyone remember? Pi over 8b squared. Now, that pi over 8 is certainly different than before. Is the b different? Is the base any different at all, changing the shape? No. So I have square root of x minus x squared all squared. For my volume, throw the pi over 8 out front if you want. If you don't want to, don't. You do you. All right. Do you think the bounds are going to be different? No. 0 and 1. So literally changing the shape, all it's going to do is just change some constants. Now, it's definitely going to have different volume. Which one do you think is going to be bigger, squares or semicircles? Squares. Can you see algebraically one of them is? Yeah, pi over 8. How big? About how? Yeah, it's definitely below 1, so that will be smaller. Let's see if I can show you. Whee! I love this graph. It's so fun. All right, I want to do more shapes too. Oh, that was not what I wanted. All right, so here's 4, here's 2, so that's our semicircles. We can see that those are a bit shorter. Hoping I could do, there's a place where you can do more than just that amount of shapes. Oh, they use polar to help. Where is it? Ah, subdivisions. Did I make this? Absolutely not. I am not smart enough to make this. I be dumb. All right, so we can kind of see a little bit more solid, a little bit more. All right, let's go ahead and finish out the X ones. So here's an example of what I could do with rectangles. So this one's saying rectangles with height equals half the base. We said rectangles were base times height. So I could just plug that 1/2 b into there and get 1/2 b squared. Again, this is not going to change anything about that base. It's going to be the same base in the XY plane, just it's going to look different going up. I'll chuck that 1/2 out in front of my integral and just use the same base that I've been doing and square it just the same. Do you think the balance will be the same? Yeah. All right, the last one. Let's see if you can remember without looking at the front page of your notes. Challenge. Isosceles right triangle with the base as the leg. Do we remember what thing went in front of b squared? 1/2 b squared. All right. Do you notice anything interesting about question number 3 and question number 4? Yeah, they're exactly the same integral. Are they exactly the same shape though, like object? No, they're actually pretty significantly different, but they would have the same exact volume. If you care about numbers, these are actually pretty darn small. So this is 0.128. This one is 0.064. Yep, and then this one's 0.050. So these are pretty darn small, but again, volume, if we're talking this small little area here and doing some little tiny volumes off of it, that doesn't seem too out of the realm of possibility. Yeah. No. So I won't ever ask you like what these look like. It's just helpful to kind of try to visualize. I actually have these things up here if anyone wants to look at them during break. Yeah, I just plugged them into the calculator using Math 9. So these are kind of cute. I inherited these from old teachers. So this is like a circle in the XY plane with some triangle cross sections. And then same circle, but some square cross sections. And then I have solid ones. So if you want to look at these during break, you're more than welcome. But right now, we're going to take a break. I'll put up a timer for 4. You have 4 minutes to yourself, and then we'll answer Matt's question of can we ever do this in terms of y? Answer, indeed. 40 minutes. That's way too long. Mm-hmm. You can also put the put it in the integral if you wanted to, so you could keep it inside.
And why was it
I don't know. I didn't make them. Wow. Breaking my things that were given to me by my AB teacher.
Not your BC teacher?
My AB teacher. I took her job too.
Taking off yourself.
To be fair, she gave me the shapes. And the job. Oh no, Miss K gave me the job, so you can blame her. I love this.
It looks like an apple back here.
One of these days I probably will. It sounds like an apple. Makes a really cool noise if you.
Is it better though?
It's really loud. Wait, hold on. Can I make it do it?
You should probably get some WD-40 for that.
There we go. You're welcome. Ooh, did I take attendance today? Probably not.
I mean, to be fair, WD-40 takes so long.
Dude, everyone is sniffling, and I don't like it.
It's
me. I would say it's me included. I mean, you're the loudest, definitely. Oh.
Well, one of the reasons it puts you to like. This is very bad poison.
Yeah. Did I do them wrong? You think so? I might have.
Oh, yeah, I just.
You would. Hello.
I don't think I did them right. No, I'm pretty convinced.
No.
Matt's claiming I did them wrong. I don't think I did. No, I agree with mine.
No.
What do we got?
No.
Alright, so you ready for today's test in psychology? You was 11, man.
How do you think you're gonna wear? I don't even know what you're wearing.
Dude, I missed more class than you, and I still don't know. Are you just gone?
Was there?
No, like mentally.
I'm always
All right. My goal is to at least get these questions done before the end of class. I would love to get this next block and this top one done. Let's see if we can make it to that. So we're gonna go back to the one we were using before, that square root of x and that x equals 9. So I'm gonna redraw that real quick. As we're redrawing it, does anyone see anything different in the question? Yeah, let's look. We got perpendicular to the y-axis. That means I have to work in terms of y. So all of my equations essentially need to be solved so that they are x equals stuff with y's in it. We need y bounds. It's going to be a whole switch of the situation. So I'm going to label some stuff. That was 9. What was the y value at that point? 9 comma what? 3, because that's the square root of 9. So if I were drawing that base that I've been drawing, this is now going to go horizontally. And you're going to notice that theme when we get back from break. We're going to start rotating things. If we ever set ourselves up horizontally, we're going to be working in terms of y. Nope, just somewhere in the region. So I like to draw mine kind of towards the middle, but you'll notice mine's a little higher than the middle right now. All right, so let's talk squares. B squared, right? All right, let's remind ourselves what side is top and what side is bottom. Let's get some physical buy-in. Which side is which? Which one is top? All right, so this side of the room, right? The higher x values are over here. So if you need to, you could label this side top. So we're going to do x equals 9 is bigger. Now, the bottom function is going to be what? Ooh, square root of x. Am I allowed to use square root of x, though? No, I need to use that equation, but it needs to be in terms of y. X equals y squared. So I'm doing 9 minus y squared. Now, if you want to check if you're subtracting in the right direction, take a y value that's in your region, say like 1, and plug it in. Do you get a positive value for 9 minus 1 squared? Yes. So we subtracted the correct direction. All right. For my volume, I'm going to chuck that guy in an integral with now dy at the end to represent the y values that we're using. B squared, my base squared. Derek's question, would the bounds be 0 and 3? Brilliant. He's using y bounds since y is in my integral. If you chuck this in your calculator, 129.6. He large. That's okay. All right, what do you think is going to change if I change this to semicircles? All right, going to change the shape, certainly. Will it change the base? No. Will it change the bounds? No. So let's skip straight to volume. What's the only thing that's going to be different? Pi over 8 in front. Hmm? All right, let's look at rectangles. Here, yeah. So I kind of I'm showing you right now what changes based on changing the shape. Next time we learn, we're going to be rotating things around different lines. The line is going to make a much bigger impact on what happens. So I kind of want you to see what is region specific. So based on what region I draw and what thing is shape specific. So that's going to represent the shape that I'm kind of building off of my graph. So you can see here we have squares being built up on that region. But if I change this shape to like something bigger, if I can make this play, this has shapes of side 34 sides. So that definitely changes the volume that we're working with. Now they're always going to tell us what shape to use, but it definitely changes the volume that we're working with. This is the semicircle. Yes. So technically not this one because this is perpendicular to the x-axis. So this is the first question we did. But yeah, they'd be like long boys going that way. Yeah. Yeah. Yeah, I've never seen them do that before, but I imagine they would give you some sort of formula for that because that's not like a well-known area formula.
And also, are we just gonna do graphs where it's just like that kind of growth?
No, so we'll do one in a second with a more complicated graph. But for anything that's kind of more complicated than like square root of x, x squared, lines, stuff like that, that's easy to graph. You would have a calculator and you'd be able to graph it with your calculator. All right, with height equal. So we got rectangles, height equal to 3 times the base. We can do h equals 3b here. So when we do base times height, we get 3b squared. Literally the only thing that's going to change, we're going to have a 3 out in front. Thrilling. So what I want you to get, this is feeling a little repetitive. I understand. I'm kind of meaning it to be that way. What I want you to understand with cross sections is so much is happening based on the region that we draw. So when I say you need to draw the region, you need to be convinced about what region you're doing. That's why so many of the decisions are based on this picture and not on the cross section itself. Yes. Yep. So we'll finish up today with one that's very specific. All right, last one. We have isosceles right triangle with the base as the hypotenuse. Anyone remember our area formula? 1/4 b squared. So for my volume, I'm chucking a 1/4 out front. I can show you. All right. So this guy was 50.893. This guy 32.4. This guy 388.8. So we have quite the range of volumes here, but again, volumes kind of get bigger faster than area does. So if I gave this one specifically to you without a calculator, I'd probably say set up but do not evaluate. So you'd set up the integral and you just leave it. Yeah, a lot of these get really nasty really fast. All right, so you guys are asking a lot of really good what-if questions about these things. So let's talk about what this will actually look like on the AP test. So this question is from 2015. We actually did the area part of this last time. This is a good example of what this would look like on the AP test. So we've got these two functions that we're going to put in the calculator in a second. So if you need a calculator, you can go grab one behind Herbie. We are looking at region S specifically. So we're looking at the right end of this graph. And let's pick out the important pieces of information. So can you look at that second paragraph and tell me what words are the most important? All right, perpendicular to the x-axis. What does that mean for me? All right, in terms of x, also, if I'm drawing this line, it's going to be going up and down. What else is important? Squares. So like Herbie was asking, it's going to be specific. It's going to tell you exactly what shape to use. All right. As we're graphing, does anyone remember what this top function was? Which one that was, f of x or g of x? Was it the e guy or the x to the fourth guy? Yep, this top guy is f of x. This bottom guy is our g of x. We could confirm that on the calculator. So you're noticing if we get a more complicated graph, these are certainly complicated. We could verify by graphing. Now, I remember this was an intersection point. I'm going to label it A right now before I go to my calculator. It was something slightly north of 1, so I'll remind us how to find that. But let's set up the integral so we can just go straight to the calculator. Actually, before I do that, let me do my area. You could. All right, so squares. What's my area formula for squares? B squared. All right. If I look at that pink line that I drew, that base, what things would I be subtracting in what order? What's my top function? F of x minus, what's my bottom function? G of x. All right. Throwing that into my integral. Again, if you're starting to not want to do the 2 steps, that's fine. I just like to separate my decision making, especially for what we're doing next time. What are your thoughts on bounds? A as my bottom one. I'll find that in a second. Derek said 2 with a question mark. Does anyone want to remove the question mark from the top bound of 2? Perfect. 2. Perfect. Again. So it's this up here. We're in S, so we can go as far left as the intersection point, as far right as 2. All right, so let's remind ourselves of some calculator stuff, and then we will be done. All right. We can if you want. I was going to save it for next time. It's a little gross.
Yeah, I'll wait.
Oh, yeah, we were graphing this. I thought it looked more like a clover. If you change the domain, it looks kind of like a butt. So you're looking at your 2 functions, and you're always subtracting the one that's vertically higher and the one that's vertically lower. So your top minus your bottom. If you're doing it in Y, you're doing right minus left.
For A again, is it where they intersect?
Yeah, so let's find that intersection point together. Real quick, I'm going to go to my graph. Can you remind me, how do I do the intersection point? Second, trace, and we're going to do number 5. First curve, you can press enter. Second curve, you can press enter. For the guess, you want to make sure you're closest to the intersection point with your kind of shiny boy, or you can do 1 and enter. Yep. So second, trace, number 5. I'm going to press enter, enter, and I know it's close to 1, so I'm going to press 1 and then enter. Now, before I do anything else, I'm going to go back to my home screen and I'm going to store that value for A. So I'm going to do second quit. I got my X in there. I'm going to store it, the button right above, on as alpha A. That'll make sure I keep it in my calculator no matter what, so that it's there. So again, X store A. I'm also going to write that number down on my paper so that I can use that A in my integral on my paper as well. So this was what we had, 8319. Yes, if you're going to use the A in your integral, you should label it on your paper as A. You don't necessarily have to do it on the graph, but you want to make sure you're telling them.
Does it matter how many points you have?
Not necessarily. I would not do less than 3, definitely. All right, so let's go ahead and plug this in. I'm going to math 9. I'm going to go alpha A up to 2. Ooh, does anyone remember how I can reference my alpha trace? Nice. Alpha trace y1 minus alpha trace y2 and squared and dx. I'm going to cross my fingers that I typed that all right. Let's see. Did anyone else get 1.283? Yep. All right. 3 decimal places per usual. Nope. So this one just had us in region S. If I wanted region R, though, absolutely. Cool. All right. We can save the. So there are some examples where I could give you a very simple region and you could do this by hand. So for example, this one right here, because this test is going to kind of come fast and furious, I am going to focus almost entirely on the setup and not the integration side of this. So for this test, when you take it, you're going to get a calculator for the whole thing. And I will probably make you integrate very, very few questions. Cool. All right, 12:46. Can we get a notes check done? 12:47, 6 minutes. All right, can we do it next time then?
Yeah.
Okay.
Let's start off.
Let's can we do a little schedule talk for next time then? Cool. All right. So some things I want to tell you about. So next class, which is Friday. Yay, finally. All right, what's happening the moment we walk into the room? Round dos. You'll have 20 minutes per use. For some of you, that will be a very exciting 20 minutes. Then we will do a notes check on 7 nope, not 7. We're in 8. 8.2 with a question from 8.1, just to review so we have that kind of in our noggins. I do have them printed, so if you want it before you leave, you can take it, but I have your new problem set. It's the last one. No, I'm not going to say that. I might give you a review one. So, new problem set. No, I couldn't find it. I don't know where it went. So I liked when you guys drew it, though. That was cute. And then we're going to do AP review to finish out our time. I do not know how I'm grading this yet, but I'm just going to warn you that our AP review will be graded. That is not going to be like out of 100% graded, though. So as we're working, I'm going to try to make it a friendly grade so that if you're showing up, you're working, you're getting a good grade on that sort of stuff. But I do want to kind of emphasize that there should be some work going into it. So it'll be friendly, but graded. So we'll be working on that AP review. Now, over spring break, there are some optional experiences that you can do if you're just like, man, I really love calculus, or if you're like, man, I really want a 5 on this AP test. You can sign up for the mock exam if you would like. I don't think any AB student has signed up for it yet. Yes. All right. If you want, if you don't even want me to grade it, you just want to come in and see what it feels like, that's totally fine. You have 3 options. One is this Saturday. So if you're like, man, I want to make it through this week and come immediately back to school on Saturday, I'm starting to regret that decision. Come regret that decision with me. Or you can come on Monday, April 18th. I've got a morning session and an afternoon session. Again, if you literally just want to come in, take it, see what it feels like, I don't have to grade it. If you want to know graded what it is, what you would get, I can also do that too. That's just there if you would like that experience. Also, I'm going to be sending you home with probably the 2012 multiple choice. This is going to be an optional grade for 4th quarter. So like an optional, probably quiz quiz or test grade. I think it's 45 questions, so I'll probably grade it out of 50 points. So that's a quiz. If you would like to practice some multiple choice, pad out your 4th quarter grade, that is going to be there for you. I'm using the 2012. It's the last one, I think, unless I can find a newer one that's fully released so you can like take it, work with it. I'll put the answers up, but essentially if you have the answers with correct work, then you'll just get a free like 100% grade on that. After we come back from break, we're going to be doing some practice more specifically with free response. We'll also be taking the Unit 8 test That usually, and I probably will go with that. I'm probably just going to give you a test bank of questions and say, hey, this is about double the amount of questions on the test. You're going to come in and take these exact questions because it's the end of the year. We're all tired. What? So I don't have a specific one scheduled right now, but if you can't make either of those, you can certainly shoot me an email and I can try to figure it out. There probably won't be another time where you can sit down and take the full like 3.5 hours. But if you want to split it a couple of days after school or a couple of mornings, we can work something out. If you fill out that Google form, there's a spot to put that information if you want. Yeah.
So, Chris, what time are you cycled?
Oh, I actually don't know if I printed them, but it's up online.
Yeah, okay.
Cool. All right. Well, we have about 2 minutes left. Hopefully, I'll see you guys on Friday. Also, remember Friday, any corrections, makeup work, makeup tests, anything like that, it should all be done Friday by 4:03 p.m. Do not email me after Friday. Cool. I'll look over them, and then I will have a test. When are you trying to come in?
Either tomorrow morning or Friday morning.